For project 2, our group selected the statics problem. This problem can be used in engineering to calculate tensions for bridges and to find the min-max of the best tension for a bridge depending on how long the ropes are that are pulling the object. Our given problem tested two different lengths and a weight and attempted to find the tension that the ropes would exert on this box over here, depending on how long the ropes were. Rope LAB was constant and LBC was changing. And so in order to find this, given these two lengths and this angle here, a combination of the sine rule and cosine rule were needed to calculate LAC as well as this angle phi over here. And using these angles, you could calculate the varying length of this rope. Of course, using MATLAB, we can use various different points, and this will expedite the process rather than doing it manually by hand. This code could of course be used further for other engineers. This algorithm sheet represents all the knowledge required to solve this problem in MATLAB. So the inputs that we are given as per the problem are the distance of length D, the mass of the block, and the length of rope AB. There are many unknowns that we need to calculate. Theta, the tension in the two ropes, as well as the length of rope BC, and also the problem asks for the maximum tension for each respective rope. So this is also something that we need, as well as the maximum length for that tension. The final values that we need are only these last three, but these other four are also needed to calculate the problem. So as mentioned before, the two main trigonometric functions that we will use are the sine rule and the cosine rule. They'll help find the various lengths needed for LBC as well as theta and phi. And after we have calculated that, we will use physics, specifically Newton's second law, to find the net force. And so we will use tensions Tx and Ty through the logic of physics to calculate that. Gravity will also be a force that is an intermediate force. So to go over the algorithm, we'll first export the Excel sheet into MATLAB, and then we'll create a range of values for LBC in MATLAB. And so we'll be checking through the loops to make sure that they're the absolute values. And if that doesn't work, then we will use a user input to make sure that they are indeed absolute values. Then the user will input a value given from 11 separate data sheets in Excel, 11 different rows of Excel values. So they'd pick 1 through 11. And then the cosine rule would be used to calculate the angle theta. Once we know the angle theta, the sine rule can be used to calculate angle phi. Once we have that, we can use force is equal to mass times gravity to find the force on the block, and the net force equations to finally calculate TAB, TBC through a system of equations. Once we have that, we can plot TAB and TBC against LBC, and if there's a reasonable trend line, that would be plotted, and of course the max function will be used in MATLAB to calculate the max TAB and TBC for the maximum length LBC. Okay, so now we will move on to the actual code in MATLAB. You may notice some discrepancies between the algorithm and the final code, but that is the nature of writing a code. What you've originally planned out in the algorithm may not remain the same when you actually use the code. So here we have the variable values that is going to read the values from the Excel spreadsheet to Excel's read, and the function size with also value c will index these values. Over here we have a for loop with k and l, and these will be index values in k and l, and basically this ensures that the values k and l that are columns in the MATLAB script will remain positive. In order to check that, we also put in some negative values to ensure that works. Then the MATLAB columns will be split up into separate columns. So one of the inputs was length d, one was the weight of the block, and the final input, as mentioned before, was the length AB. So here, as said, we will check the geometry and make sure the distances actually make sense. And in order to do that, we will use the geometric rules that the sum of two sides have to be longer than one side in a triangle. So here we will use k as an index value that runs through 1 through r, as mentioned here as well, and it'll make sure that all values LAB are bigger than d, because they have to be bigger than d for it to make sense in a triangle. And if it isn't, then there'll be an input statement that asks the user to actually put a more reasonable value. Finally, here we have the empty set LBC, which is going to be assigned using the geometric rules that I told you here. So here we are establishing the minimum LBC by subtracting one of the lengths with the other, and the maximum by adding the two. And we added +1 -1 because we know it's not going to be exactly equal to that value, but a little less. Step is the function that we will use a little bit later, and so LBC will be defined from the minimum to the maximum by the step over here. Then LBC will also be transposed because we're flipping from column. So here the user will be asked to input a value 1 through 11 that corresponds to a value on the Excel spreadsheet. This will attempt to find many different ways to ensure that they enter the right value. So here LBC, D, W, and LB are assigned depending on the Y index that the user picked. And so now we enter our function static fun. So here we begin the calculations that I mentioned in the algorithm sheet. So force will be calculated by multiplying weight by gravity, and length is also assigned. TAB and TBC are assigned as an empty set. So here we have basically the cosine rule split up into parts A and B and then divided out here. Theta is then used by calculating cosine of that length, and then theta is converted into degrees. Here we have we're trying to find phi, so again we're using the length over here, and now we are calculating the values cosine p, cosine t, sine p, and sine t, and assigning them as functions. So they're all put into this value a, and b is then used as an identity matrix, because we basically have a 2x2 and a 2x1 matrix that we're going to multiply out to get TAB and TBC, because it's a system of equations, and our group thought it was appropriate to use matrices as the best way to calculate the answer. So now we'll go back to the main script. Maximum TAB is found by using the max function, and using that index value in the max function, you can find the maximum length for BC. Same is done for length BC, and sorry, first we use it for AB and then for length BC. Finally, we have our values, and we do that. we'll attempt to run the MATLAB program. So here, as mentioned in the code, the user will be asked to input a value. So let's just pick 4. And so an fprintf statement will output the maximum tension for AB in newtons and the corresponding length for that. It does it for both length AB and BC and calculates the respective tensions. And so this graph here shows, using the geometric knowledge that we have, the range from the minimum length to the maximum length on both graphs and the tension. As you can see, it doesn't appear that there is any logical trend, and so perhaps that is a limitation in the code. Let's pick another value, and here we go. It seems that mostly they're linear curves, some power curves, with a few outliers every now and then. It may be that these are critical points in the structure where the tension's too high and only one rope is pulling. For the most part, this code is very basic and seems very limited. It could be used as a backbone to make a more powerful code. But as it stands now, it's just a very basic code. Many actual engineers, structural engineers who may use this for respective ropes and stuff will often have a series of ropes pulling a bridge, or pylons pulling concrete, and just one tension isn't really that valuable. Aside from that, it is a very important code and could be used for very basic applications in engineering.